Negative cycles in a graph. So far in our consideration of the Bellman-Ford algorithm, we have assumed that the underlying graph has negative edge costs but no negative cycles. We now consider the more general case of a graph that may contain negative cycles. The problem: there are two natural questions we will consider. How do we decide if a graph contains a negative cycle? How do we actually find a negative cycle in a graph that contains one? The algorithm developed for finding negative cycles will also lead to an improved practical implementation of the Bellman-Ford algorithms from the previous sections. It turns out that the ideas we've seen so far will allow us to find negative cycles that have a path reaching a sinc t. Before we developed the details of this, let's compare the problems of finding a negative cycle that can reach a given t with the similarly more natural problem of finding a negative cycle anywhere in the graph regardless of its position related to a sinc. It turns out that if we developed a solution to the first problem, we'll be able to obtain a solution to the second problem as well in the following way. Suppose we start with a graph G, add a new node T to it, and connect each other node V in the graph to node T via an edge of cost 0, as shown in figure 6.25. Let us call the new augmented graph G prime. 6.29. The augmented graph G prime has a negative cycle C such that there is a path from C to the sinc T if and only if the original graph has a negative cycle. Proof: assume G has a negative cycle, then this cycle C clearly has an edge to T in G prime, since all nodes have an edge to T. Now suppose G prime has a negative cycle with a path to T. Since no edge leaves T in G prime, this cycle cannot contain T. Since G prime is the same as G aside from the node T, it follows that this cycle is also a negative cycle of G. So it is really enough to solve the problems of deciding whether G has a negative cycle that has a path to a given sinc node T, and we do this now. Designing and analyzing the algorithm. To get started thinking about the algorithm, we begin by adopting the original version of the Bellman-Ford algorithm, which was less efficient in its use of space. We first extended the definition of OPT of IV from the Bellman-Ford algorithm, defining them for values I which is greater than or equals to n, with the presence of a negative cycle in the graph. 6.22 no longer applies, and indeed the shortest path may get shorter and shorter as we go around a negative cycle. In fact, for any node V on a negative cycle that has a path to T, we have the following. 6.30 If node V can reach node T and is contained in a negative cycle, then the limit of OBT of IV, where the limit is taken among all I when I goes to infinity, is equals to minus infinity, negative infinity. If the graph has no negative cycles, then 6.22 implies following statement. 6.31 If there are no negative cycles in G, then OPT of IV is equals to OPT of n minus 1V for all nodes V and all I which is greater than or equals to n. But for how large an I do we have to compute the values OPT of IV before concluding that the graph has no negative cycles? For example, a node V may satisfy the equation OPT of n V equals to OPT of n minus 1V and yet still lie on a negative cycle. Do you see why? However, it turns out that we will be in good shape if this equation holds for all nodes. 6.32 There is no negative cycle with a path to T if and only if OPT of nV is equals to OPT of n minus 1V for all nodes V. Proof: Statement 6.31 has already proved the forward direction. For the other direction, we use an argument employed earlier for reasoning about when it's safe to stop the Bellman-Ford algorithm early. Specifically, suppose OPT of nV is equals to OPT of n minus 1V for all nodes V. The values of OPT of n plus 1V can be computed from OPT of nV, but all these values are the same as the corresponding OPT of n minus 1V. It follows that we will have OPT of n plus 1V equals to OPT of n minus 1V. Extending this reasoning to future iterations, we see that none of the values will ever change again. That is, OPT of IV is equals to OPT of n minus 1V for all nodes V and for all I which is greater than or equals to n. Thus, there cannot be a negative cycle C that has a path to T. For any node W on the cycle C, 6.30 implies that the values OPT of IW would have to become arbitrarily negative as I increased. Statement 6.32 gives an big O of M a method to decide if G has a negative cycle that can reach T. We compute values of OPT of IV for nodes of G and for values of I up to N. By 6.32, there is no negative cycle if and only if there is some value of I which is less than or equals to N, at which that OPT of IV is equals to OPT of I minus 1V for all nodes V. So far we have determined whether or not the graph has a negative cycle with a path from the cycle to T, but we have not actually found the cycle. To find a negative cycle, we consider a node V such that OPT of MV is not equal to OPT of M minus 1V. For this node, a path P from V to T of cost OPT of MV must use exactly n agencies. We find this minima cost path P from V to T by tracking back through the subproblems. As in our proof of 6.22, a simple path can only have m minus 1 agencies, so P must contain a cycle C. We claim that this cycle C has negative cost. 6.33. If G has n nodes and OPT of MV is not equal to OPT of M minus 1V, then a path P from V to T of cost OPT of MV contains a cycle C and C has negative cost. So proof. First observe that the path P must have n agencies as OPT of NV is not equal to OPT of M minus 1V, and so every path using M minus 1 agencies has cost greater than that of the path P. In a graph with n nodes, a path consisting of n agencies must repeat a node somewhere. Let W be a node that occurs on P more than once. Let C be the cycle on P between two consecutive occurrences of node W. If C were not a negative cycle, then deleting C from P would give us a VT path with fewer than n agencies and no greater cost. This contradicts our assumption that OPT of MV is not equal to OPT of M minus 1V, and hence C must be a negative cycle. 6.34. The algorithm above finds a negative cycle in G if such a cycle exists and runs in big O of M n time. Extension. Improve the shortest paths and negative cycle detection algorithms. At the end of section 6.8, we discussed a space-efficient implementation of the Bellman-Ford algorithm for graphs with no negative cycles. Here, we implement the detection of negative cycles in a comparably space-efficient way. In addition to the savings in space, this will also lead to a considerable speed up in practice even for graphs with no negative cycles. The implementation will be based on the same pointer graph P derived from the first edge, that is V and the first of V, that we used for the space-efficient implementation in section 6.8. By 6.27, we know that if the pointer graph ever has a cycle, then the cycle has negative cost and we are done. But if a G has a negative cycle, does this guarantee that the pointer graph will ever have a cycle? Furthermore, how much extra computation time do we need for periodically checking whether P has a cycle? Ideally, we would like to determine whether a cycle is created in the pointer graph P every time we add a new edge VW with first of V equals to W. An additional advantage of such instant cycle detection will be that we will not have to wait for n iterations to see that the graph has a negative cycle. We can terminate as soon as a negative cycle is found. Earlier we saw that if a graph G has no negative cycles, the algorithm can be stopped early if in some iteration the shortest path values M of V remain the same for all nodes V. Instant negative cycle detection will be an analogous early termination rule for graphs that have negative cycles. Consider a new edge VW with a first of V equals to W that is added to the pointer graph P. Before we add VW to the pointer graph has no cycles, so it consists of paths from each node V to the sink T. The most natural way to check whether adding HVW creates a cycle in P is to follow the current path from W to the terminal T in time proportional to the length of this path. If we encounter V along this path, then a cycle has been formed, and hence by 6.27, the graph has a negative cycle. Consider figure 6.26 for example, where in both A and B the pointer first of V is being updated from U to W. In A, this does not result in a negative cycle, but in B it does. However, if we trace out the sequence of pointers from V like this, then we could spend as much as big O of n time following the path to T and still not find a cycle. We now discuss a method that does not require an big O of n blow up in the running time. We know that before the new HVW was added, the pointer graph was the directed tree. Another way to test whether the addition of VW creates a cycle is to consider all nodes in the subtree directed toward V. If W is in this subtree, then VW forms a cycle. Otherwise, it does not. Again, consider the two sample cases in figure 6.26. To be able to find all nodes in the subtree directed toward V, we need to have each node V maintain a list of other nodes whose selected edges point to V. Given these pointers, we can find the subtree in time proportional to the size of the subtree pointer pointing to V, at most big O of n as before. However, here we will be able to make additional use of the work done. Notice that the current distance value m of x for all nodes x in the subtree was derived from node V's old value. We have just updated V's distance, and hence we know that the distance values of all these nodes will be updated again. We'll mark each of these nodes x as dormant. Delete the h x first of x from the pointer graph, and not use x for future updates until its distant value changes. This can save a lot of future work in updates, but what is the effect on the worst case running time? We can spend as much as big O of n extra time marking nodes dormant after every update in distances. However, a node can be marked dormant only if a point had been defined for it. At some point in the past, still the time spent on marking nodes dormant is at most as much as the time the algorithm spends updating distances. Now consider the time the algorithm spends on operations other than marking nodes dormant. Recall that the algorithm is divided into iterations, where iteration I plus 1 processes nodes whose distance has been updated in iteration I. For the original version of the algorithm, we showed in 6.26 that after I iterations, the value m of v is no larger than the value of the shortest path from v to t using at most I edges. However, with many nodes dormant in each iteration, this may not be true anymore. For example, if the shortest path from v to t using at most I edges starts on h equals to vw and w is dormant to this iteration, then we may not update the distance's value m of v, and so it stays at a value higher than the length of the path through the h vw. This seems like a problem. However, in this case, the path through h vw is not actually the shortest path, so m of v will have a chance to get updated later to an even smaller value. So instead of the simpler property that held for m of v in the original versions of the algorithm, we now have the following claim. 6.35. Throughout the algorithm, m of v is the length of some simple path from v to t. The path has at least I edges if the distance value m of v is updated in iteration I, and after I iterations, the value m of v is the length of the shortest path from for all nodes v where there is a shortest vt path using at most I edges. Prove the first pointers maintain a tree of paths to t, which implies that all paths used to update the distance values are simple. The fact that updates in iteration I are caused by paths with at least I edges is easy to show by induction on I. Similarly, we use induction to show that after iteration I, the value m of v is the distance on all edges on all nodes v where the shortest path from v to t uses at most I edges. Note that nodes v where m of v is the actual shortest path distance cannot be dormant, as the value m of v will be updated in the next iteration for all dormant nodes. Using this claim, we can see that the worst-case running time of the algorithm is still bounded by big O of mn. Ignoring the time spent on marking nodes dormant, each iteration is implemented in big O of m time, and there can be at most n-1 iterations that update values in the array m without finding an active cycle, as simple paths can have at most n-1 ages. Finally, the time spent marking nodes dormant is bounded by the time spent on updates. We summarize the discussion with the following claim about the worst-case performance of the algorithm. In fact, as mentioned above, the new version is in practice the fastest implementation of the algorithm, even for graphs that do not have negative cycles, or even negative cost ages. 6.36. The improved algorithm outlined above finds a negative cycle in G if such a cycle exists. It terminates immediately if the pointer graph P of first of V pointers contains a cycle C, or if there is an iteration in which no update occurs to any distance value M of V. The algorithm uses big O of n space, has at most n iterations, and runs in big O of mn time in the worst case.